So I welcome you all to this third lecture session, and this particular session is on macroscopic pool and flow boiling. So typically when we study the phenomenon of boiling heat transfer, it involves lots of bubble dynamics, and typically if we try to study the bubbles from the fundamental perspective, then we will be referring to phenomenon as microscopic approach. But over here, when our interest is not into look into the minor details, but if our interest is to quantify the global parameters which are associated with the boiling heat transfer, then we will be referring to the phenomenon as macroscopic phenomenon. And when we talk about the boiling, of course, if you many times or daily when we say prepare tea, then we put certain amount of water in our pan and then we heat it over the gas stove. And on the gas stove, initially there will be formation of small bubbles, and with the progress of the time we will be finding that a large number of bubbles will be developing, which will be making the interfacial structures very complex and chaotic. So from appearance wise, this phenomenon is very complex. In the similar way as appearance wise it is complex, it is also complex from analysis point of view, because all these bubbles which are interacting with the heating surface and the surrounding liquid, these are leading to significant changes on the heat transfer characteristics of the phenomenon. So typically when we fundamentally talk about the boiling heat transfer, we first define the necessary condition which we need to satisfy for boiling phenomenon to occur, and that necessary condition is that surface temperature should be greater than the saturation temperature at the given pressure. So for example, when we do heat water in a pan, then our pan is normally open to the atmospheric pressure conditions, and corresponding to that the saturation temperature of the water is 100 degrees Celsius. So if we have to boil the water, we have to increase the temperature of the heat transfer surface above than the 100 degrees Celsius. Thermodynamically, it should take place at 100 degrees Celsius itself, but whenever we go for the practical conditions, we find that we have to heat the surface temperature 10 to 15 degrees above the saturation temperature, and then only we see the bubble formation initiates. Similarly, if you consider any other higher pressure conditions, for example, whenever we heat the water inside a pressure cooker. So typically pressure cooker operates from 2 to 3 bar pressure conditions, and our boiling temperature is in the range of 120 to 130 degrees Celsius. So this point is very clear to us. Whenever we will be considering any type of working fluid, its saturation temperature is a strong function of the pressure. So the temperature of the heating surface which we need to maintain, that will be actually controlling the phenomenon of boiling heat transfer. Now this is all about boiling. Now boiling, typically whenever the initial studies of boiling have come historically, so some of the fundamental initial studies were related to first the pool boiling phenomenon, and later on then it has shifted towards the study of flow boiling heat transfer depending upon our application. In terms of application, if you see, the applications of boiling heat transfer are plenty. For example, every day we heat the water, then most of the electricity which we are getting is from actually coal based thermal power plants or either nuclear power plants. So there we are having the boilers, water tube boilers or fire tube boilers, and depending upon the different conditions and design and configurations of the boiler, we are having different complicated regimes of boiling heat transfer associated. Every day we are using air conditioners, refrigerators in our home. So inside that we have some evaporators, we have some condensers where phase change from liquid to vapor or vapor to liquid is actually taking place. So historically, if we see some of the pioneer work in the boiling heat transfer is done by Nukiyama, and in Nukiyama's experiment, this was the experimental configuration which was used. So Nukiyama was having one electric wire. So initially he started with a nichrome wire, and with the nichrome wire he started heating the water, and that water was contained inside a container, and bulk of the water was under the stationary condition. So, whenever the water is under the stationary condition, corresponding to that whatever the boiling phenomenon will be occurring, we refer typically it as pool boiling heat transfer. In Nukiyama's experiment, the nichrome wire is used for two purposes. First purpose was, it was used as heat transfer surface on which boiling phenomenon will be taking place, and the second purpose was, it was also used as resistance type temperature measurement device. So, temperature was also measured using the wire by measuring the resistance of this wire itself. So, typically we know that if we have some conductor and if I define resistance as ratio of voltage by current, then the resistance will be increasing when the temperature of the wire will be actually increasing. So, what can be done? We can do calibration of the resistance of the wire with the known value of the temperature, and then by just knowing the value of resistance we can actually back calculate the value of temperature. So, when Nukiyama conducted this experiment, because in case of boiling heat transfer it is extremely challenging to control the temperature of the heat transfer surface. So, he tried to control actually the heat flux as the independent parameter. So, in his experiment the independent parameter was heat flux, and in some of the literature if you see, so typically nowadays whenever we plot the boiling curve, we plot heat flux along the ordinate and temperature difference along the abscissa. But some of the old literature, they typically present Nukiyama's boiling curve by plotting heat flux along the x-axis and by plotting the temperature difference, which is Ts minus T sat, along the y-axis. So, in the Nukiyama's experiment, it was observed that whenever initially the amount of heat flux was increased, then heat flux has increased rapidly and the temperature rise was very less. And after a point, all of a sudden temperature has actually jumped at certain heat flux condition, and after that his wire was completely melted and he couldn't even obtain the curve after this point. Then later on Nukiyama has shifted this nichrome wire with the help of a platinum wire, and platinum was typically having the melting temperature higher in comparison to the nichrome. So, when he repeated the experiment, he found that this type of jump was taking place, and after the jump again the situation came where heat flux has started increasing rapidly, and also the temperature increase was slightly significant in comparison to what was observed in the previous case. Then we can consider that, so maybe we can join this curve with some dotted line. But whenever the same experiment was performed in the reverse direction, in the reverse direction means initially the flux was maintained at towards the higher side and then gradually it is actually decreased. So, upon doing that, he observed that this curve was exactly following this condition over here, but later on this phenomenon has continued to some minimum value of the heat flux, and after this minimum value of the heat flux there was sudden drop in the temperature, and then it was again behaving like it has earlier behaved. So, it means that during the heating there is this point, and after this point something was happening over here, and during the cooling process this point has, boiling process has continued below some limit and then it has actually fallen down. But in his experiment, because he couldn't control the temperature, so in between what is happening, that was not obtained. However, he has given some idea that in between this we can typically join this with the help of some dashed line. Okay. But later on then what was done, Drew and Muller, they tried to perform the boiling experiment by controlling the temperature of the heating surface. So, here controlling parameter was the temperature of the heating surface. So, how they did control the temperature, because controlling the temperature is quite challenging. Once your heated surface is in contact with the liquid phase, then the rate of heat transfer will be at the faster pace, and whatever your input heat supply, that has to be increased in order to maintain the same temperature condition. But if it is being contacted with the vapor, then the rate of heat transfer will be decreasing, and if we have to maintain the wire at the same temperature condition, then we have to also decrease the input supply. And this phenomenon is intermittent, and it is sometimes quite fast and chaotic, and that is why it is extremely difficult to control the temperature. So, what they have done, basically they have employed a steam tube apparatus. So, they have employed a steam tube apparatus to perform the boiling under the constant temperature conditions. So, what is done? A tube is considered, and inside this tube steam was allowed to flow at saturated conditions. So, say you are having saturated vapor which is entering this tube. What will be happening? Whenever this saturated vapor will be flowing, if it is supplying the heat to the liquid in which this tube is submerged, during that process, this working fluid, which is steam, it will be actually losing the heat in the form of its latent heat of vaporization. And if we are able to control that, we will not go below the saturated liquid conditions, we will not enter into the subcooling regime, then the temperature from this point to this point will be remaining almost close to the surface temperature. Now, outside, what we need to do, we need to use the working fluid which is having boiling point equal to that of the saturation temperature of this steam at the given pressure condition. So, many of these experiments are actually done with the organic fluids, because typically at the atmospheric pressure conditions their boiling point was less. And this is how actually the constant temperature regime, some of the data points were obtained at different pressure conditions, and then the constant temperature boiling curve was actually obtained. So, typically if we see, this is the boiling curve which we will be obtaining once we are actually independently controlling the surface temperature of the heat transfer surface. So, here you can see along the abscissa we have heat flux, and here we have Tw minus T saturation. Now, because the independent parameter is over here temperature, so it is plotted along abscissa. And in this boiling curve, you can see there are different regimes. One is from A to B to C. So, from A point to C point, we do not have formation of any type of bubble, and this type of boiling regime, in this type of boiling regime, whatever the heat transfer will be taking place, that will be taking place in a purely single phase regime. And as the pool is stationary, so that is why natural convection currents will be developing within the pool, and these will be leading to the heat transfer process. And we know that in the natural convection process, if our temperature difference is increasing, then we will be having corresponding increase in the heat transfer rate, because heat flux will be proportional to the temperature difference. And that is what we are observing. Whenever we are moving towards the higher temperature difference, then we are getting our heat transfer is actually increased. From point C, one interesting jump is there. So, typically some of the books, they show that from B point to D point we will be having some jump, but in some of the textbooks we will be finding that there will be from C point onwards we will be finding that bubble formation initiates. So, this is the point where bubble formation initiates. So, we typically refer to this process as onset of boiling, because before this point it was only taking place in the single phase regime. After this point actually formation of the bubble started. So, this is the onset of boiling. So, at finite number of finite number of nucleation sites on the heated surface, we will be finding that some vapor volume will start forming. Now, initially the size of these bubbles is actually very, very small, and surface tension forces will be large enough, and these will not be allow the this vapor volume to leave the nucleation site. Slowly, the size of these bubbles will be actually growing with time, and once their size is sufficient enough, like body forces, buoyancy forces are sufficient enough to overcome the surface tension forces, then this will be actually leaving the heated surface. So, this type of regime where a bubble forms at the nucleation site and then it leaves the nucleation site, that is typically called as nucleate boiling, and the regime from point C to point F over here is our nucleate boiling regime. Now, this nucleate boiling regime can be divided into two parts. One is the isolated bubble regime and second is regime of slugs and columns. So, in case of isolated bubble regime, the number of bubbles which are forming on the heater surface are less, and these bubbles, because once they have their buoyancy forces are sufficient, these will be leaving the surface and then some new bubbles will be actually forming at the surface. But slowly we will be finding that if we go towards the higher temperature difference, then more number of nucleation sites will be activating on the surface, and we will be having formation of large number of bubbles. And these large number of bubbles, as because periodically these are leaving the surface, we will be finding that two or more bubbles from different nucleation sites will be merging together and forming a big vapor volume, and which will be rising in the form of slugs and columns. And in this regime, typically we have the highest heat transfer rates. One interesting point is, here you can see the jump from C point to D point is because whenever bubble forms, it carries, because of the buoyancy force, it leaves the surface. So, once bubble is leaving the surface, it re-wets the liquid surface, because whatever the liquid was ahead in the path of the bubble, that will be actually now occupying its space. So, that liquid will be re-wetting the surface. Because of this, nucleate boiling is having some additional heat transfer coefficient in addition to the natural convection boiling, and that is why we have this sudden rise in the heat flux. Now, we will be getting a situation which is our highest heat flux condition, and after this highest heat flux condition, slowly we will be finding that our heat flux value will keep on decreasing. So, typically the regime in which this heat flux decreases and reaches a minimum value, that is called as actually transition boiling regime. So, what happens in transition boiling regime, now the nucleation site density has increased significantly, large number of bubbles are forming, and these bubbles, once they are leaving the surface, ultimately these are leading to large portion of heat transfer surface covered with vapor, and typically vapor is having low thermal conductivity in comparison to the liquid. So, the heat carried by the overall fluid will be actually decreasing significantly. And after this point, because after this point our rise in temperature is significantly high. So, in addition to the conduction and convection effects which are taking place with the liquids, the radiation heat transfer effect will also be contributing significantly, and again we will be finding that we are having significant rise in heat transfer characteristics. So, typically whatever the boiling regime or boiling pool boiling map we are presenting over here, this map does not work for all the type of surfaces, because here we are specifically talking about the wettability. So, typically the conventionally studied pool boiling regimes or boiling maps were applicable for hydrophilic surfaces. So, if we change the wettability, of course, all the regimes are not going to change, but there will be some characteristic changes in some of the specific regimes which can be actually tuned by the wettability. Second important point is, here two important length scales are involved. One is the say length or size of heater, and another one is the size of the bubble. So, say LB is size of the bubble. So, typically the size of the bubble, because it is balanced by the combination of surface tension and the buoyancy forces. So, I can say that if delta rho is density difference between liquid and vapor, G will be my gravitational field, and I will be having, say, if LB is the length scale corresponding to the size of the bubble, then delta rho G LB cube will be my buoyancy force and surface tension force will be sigma times LB. From here I will be finding that my length scale is nothing but equal to sigma divided by delta rho into G. So, whatever the boiling curve which we have defined over here, it is applicable when length of the heater surface is significantly large in comparison to the size of the bubble. In case we are operating in the regime where LB is greater than L, in that scenario what will be happening? The entire heater periphery, for example, if you consider that we are doing boiling of water under atmospheric pressure condition on a thin wire of 1 millimeter size or so, 1 millimeter diameter or so. So, we know that capillary, this length scale LV is close to 2.7 mm for the water at atmospheric pressure condition. So, if I will be using a wire of 0.5 millimeter or 1 millimeter diameter, the majority portion of the wire will be covered with the vapor volume. So, we will not be able to achieve the nucleate regime, rather we will be actually soon shifting to the film boiling regime. So, that is one important point, that whatever the length scales which we are actually dealing with. So, typically the conventional boiling curve which we study in all our undergraduate courses, this is defined for wettable surfaces which are having good hydrophilic characteristics, and second important point is that length scale of the heating surface is significantly larger in comparison to the length scale of the bubble. Yes, yes. But typically, whenever we are in this particular regime, the isolated bubble regime. So, in isolated bubble regime, what will be happening? We will be having nucleation of the vapor and small vapor volume will be generated. But if surface forces are significantly large in comparison to the buoyancy forces, that bubble cannot leave the surface. Slowly it will be growing in size, and once buoyancy is dominating, then it will be leaving the surface. Now, this is the pool boiling curve which is actually having two transition curves. So, again the temperature controlled experiment, but now temperature controlled experiment is first in the forward direction when we started from the lower temperatures and then we entered into the high temperature regime. And in the second scenario, we started from the high temperature conditions and then in the reverse order we have moved towards the low temperature conditions. So, two different distinctions are observed. One is the change in this portion and second is the change particularly in the transition boiling regime. So, in case of transition boiling, so first let us talk about this point. So, typically whenever a nucleation site is activated, it requires some critical degree of superheat for the vapor volume to nucleate at a particular site. And whenever we are actually moving in the reverse direction, then what will be happening? We typically observe that when the bubble leaves the surface, there is this neck formation, and after the neck, a small amount of vapor residue remains attached to the surface. So, because of this residue, because already it is having the interface from where nucleation can grow, so what typically happens when we move in the reverse direction, whatever during the forward direction we were having the minimum temperature condition, even below that also if vapor volume is there, nucleation actually can be sustained. So, that is the reason we obtain this difference during the cooling, that even up to point E we will be having the nucleation of the boiling, even though its temperature is less in comparison to the minimum temperature required to activate a nucleation site. Second important point is This transition boiling curve during the forward direction it was having higher heat flux, and during this particular cooling time it is having actually lower heat flux values. Why so? Because the transition boiling regimes is the one in which phenomena is switching in between the nucleate regime and the film boiling regime. So, sometimes I will be finding that on the heater surface two bubbles are actually merging together and forming a larger vapor chunk, and sometime it can happen that the vapor chunk while it is leaving it will re-wets the surface, and because of the re-wetting of the liquid this particular vapor volume can move in the inward direction. So, here you can observe that when two vapor volumes are forming and these are moving in the outward direction, basically over here our contact line is actually advancing. So, if we have advancing contact line, so over here the angle which will be applicable, that will be advancing contact angle theta A. On the other hand, when this vapor film is broken and liquid is re-wetting the surface, then this vapor volume is displaced in such a way so that the contact line is actually moving towards the vapor side. So, it means this contact line is actually receding. So, typically when phenomenon is that from the film boiling we are shifting towards the nucleate boiling regime, my vapor film will be broken at multiple places, and this liquid while it is re-wetting the surface it will be moving the vapor volume in the inward direction, which means it is actually the phenomenon is taking place with receding contact angle theta r. On the other hand, when phenomenon is shifting from the nucleate boiling regime to the film boiling regime, then multiple bubbles are displacing the liquid. It means these are advancing in such a way so that these can form a vapor blanket. So, because of this contact line dynamics over here, we will be finding that the heat flux, or we will be having significant difference in this particular transition boiling regime. So, you can one clear observation is that wettability will be significantly controlling the transition boiling regime. Now, the boiling curve with the heat flux controlled experiment. So, again the same Nukuyama's boiling curve, but with more experimental data, so more details. So, here we see then this natural circulation, natural convection boiling regimes extend up to C, and C is the point where we will be having actually vapor formation. After vapor formation, once the vapor volume will be actually leaving the, leaving the surface, then there will be significant re-wetting of that portion, and that re-wetting actually will be creating residue for the next bubble to grow. So, that is why there will be sudden drop in temperature because of the re-wetting. Now, because there is a vapor residue, so because of that vapor residue, nucleation can occur at the low temperature itself. So, from D point it will be actually moving in the upward direction. And whenever we operate this up to the highest heat flux point, which typically is either known as peak heat flux or critical heat flux or even sometimes burnout heat flux, after this point we will not be able to actually achieve this portion of the curve which we were able to achieve in the temperature controlled experiment, and here we will be experiencing a sudden jump, and then we will be entering into the flow boiling in the film boiling regime. So, maximum time whenever we design our industrial systems, always our idea is to operate at the high heat transfer conditions. Okay, because if our heat transfer rate is high, heat flux is high, the size of the system will be less and we will be having less capital investment. And many times if you are talking about you have a smaller boiler, then you have to pump water in the smaller boiler tube, so pumping power will also be decreasing significantly. So, our interest is to operate in the peak conditions. But another one important point is, if we operate under the peak conditions, there can be sudden rise of the temperature and there can be melting or failure of the component. And typically for the nuclear industry, because they are controlling the heat flux is extremely difficult, their rapidly heat flux actually grows. So that's why we have to operate in the conditions where we are far below the peak heat flux conditions, because if we operate near the heat flux peak heat flux conditions, then all of a sudden rise in temperature can take place, which ultimately may lead to the failure of the equipment. Then this is the boiling curve for decreasing heat flux. So for example, if I operate at high heat flux and after that I keep on decreasing the value of the heat flux, so after reaching this, then this transition regime is completely eliminated, and all of a sudden we experience sudden decrease in the surface temperature, and again we will be having decrease somewhat like this. And here also the starting point where we were heating, we were going up to this point, but now nucleation is sustained up to point D because of the presence of the vapor residue. Again, another important parameter is, though we say that whenever we are operating under the pool boiling conditions, we have to keep the bulk liquid at the saturation temperature conditions. But majority of the time, it also happens that we are not using any secondary heater for heating our pool. So if we are not using any secondary heater for heating our pool, and we are only using the heater from where we want to study the boiling for heating the entire pool, then it may happen that the liquid which is available close to this bottom heated surface, it will be under the saturated conditions, but further away from this we may have bulk at the subcooled conditions. So always we know that whenever we are having the subcooled conditions, in natural convection we will be getting the larger temperature difference. So because of larger temperature difference, of course in subcooling we will be having high subcooled pool boiling, we will be having higher heat transfer rates in comparison to saturated boiling. But in the nucleated boiling regime, effect of subcooling is actually very less. The reason is nucleated boiling regime in itself, it has so high heat transfer characteristic that the temperature difference is not able to make the significant change, which typically takes place in case of natural circulation heat transfer. Now, in case of nucleated boiling, because typically what is the reason for decrease of heat flux after this peak point? The reason is whenever two columns of vapors are rising, say this is vapor, this is again vapor, and in between these two columns of vapor we will be having liquid. So when these two columns of vapors are rising, these will be having some interesting instability formation, and under certain critical conditions the amplitude of these may rise, and even these will be actually decreasing the amount of area which is available for water to move in the downward direction. So water will not be able to re-wet the surface. But if we have more amount of subcooling, then ultimately what will be happening, whatever these columns are rising, most of the vapor from top portion of the column can immediately condense once it reaches into the subcooled water. So because of this, the amount of volume of vapor for this instability to grow will not be sufficient. So that's why in the subcooled flow boiling condition we can achieve the value of critical heat flux higher in comparison to the saturated pool boiling conditions. And of course in this part is significantly dependent upon the continuous re-wetting and non-wetting. So here it will be changing a lot, but again in the film boiling regime, once we enter, then we will not be able to experience much changes because of subcooling of the pool. This is again now the effect of forced convection. So now we are not limiting ourselves to pool boiling, but we are slowly entering into the flow boiling regime. So typically, if we consider the majority of our heat transfer equipment, for example, our heat exchangers, evaporator, condensers, etc., there water or working fluid has to translate from one location in the tube to the other location. So, because of this, the stagnant pool cannot be maintained, and we will be having requirement of continuous flow of the working fluid, for example, in our coal based or nuclear based thermal power plants or in refrigeration cycles. So, because of this, we have to continuously flow the fluid. So, once we are continuously flowing the fluid, we will be having actually now the velocity of the fluid which will be coming into picture. So, because of the velocity, we will be actually calling this phenomenon as forced convection. And if we compare this with the pool boiling conditions, in case of forced conditions, we will be having high heat flux in the single phase regime. We will be having higher value of the peak heat flux, because what velocity can do, velocity can displace the large amount of vapor. So, that is why the formation of the chunk of the vapor can be delayed to higher heat flux conditions. So, because of this, we will be having actually significant rise in the peak heat flux conditions. And in nucleate boiling regime and film boiling, of course, in film boiling regime we will be having some increase in the heat flux, but typically in the nucleate boiling regime, the rise in the heat flux is not significant. So, one thing about the nucleate boiling regime, we can say that in most of the conditions, it is the one which is contributing significantly to the rate of heat transfer. Effect of wettability, of course, as I told you, mostly it will be applicable for the transition regime. And in the transition regime, if I move towards the hydrophobic or super hydrophobic conditions, where contact angles are close to 180 degrees, then mostly boiling can sustain in the film boiling regime only, even at the low temperature conditions, because liquid will not be getting opportunity to wet the surface because of the surface characteristics. And as we will keep on decreasing the angle, like we are entering towards the hydrophilic condition where liquid has chance to wet the surface, our boiling regime will try to shift towards the nucleate boiling conditions. So, from this point, we can make one observation that there are 4 important factors which typically controls the boiling heat transfer. The first point is surface characteristics. How surface characteristics are important, probably in today's lecture I will not discuss much, but in terms of surface characteristics I can only say that the number of nucleation sites which are forming, this typically depends upon the surface characteristics. In my next lecture, when I will be talking about onset of nucleate boiling, there we will be studying these surface characteristics in more detail. Second important point is thermophysical properties. So, of course, whatever the fluids we are having, their thermophysical properties plays an important role. For example, water at an atmospheric pressure condition, we have to raise the temperature above 100 degrees Celsius, but if we have to heat a refrigerant, it may so happen that at atmospheric pressure condition, it may boil at -10 or -11 degree Celsius, depending upon the thermophysical properties. Third important point is, we have also decided what is our configuration. So, in most of the cases, we were assuming that our configuration is ideal, like purely wettable or hydrophilic, but if we change the wettability, then some of the regimes of boiling heat transfer will be actually changing significantly. And it is also important to know that the relation between length scale of the heating surface and the length scale of the bubble which will be nucleating at a particular condition, that is also significantly controlling our boiling heat transfer conditions. Now, whatever is happening in the pool, that is sometimes easy to visualize because it is happening externally. But when the same boiling phenomenon we have to actually do inside the surfaces. For example, you have a tube inside the evaporator tube, there is a copper tube which is curved in certain way, and there refrigerant is flowing at one point in the mixture state or say saturated liquid state, and finally it is going either to the saturated vapor or the superheated condition. So there what will be happening inside the tube, for that we will be actually studying the heat transfer coefficient and the flow boiling regime characteristics, typically with one important parameter which is known as quality. So with quality I mean that we are talking about fraction of vapor mass present in the system, because typically we define the quality as mass of vapor divided by total mass of the mixture. So typically what happens, if I have, so this of course flow regime map in different type of tube configuration, it will be having different characteristics. We will over here try to see it for two simple situations. One is situation of a horizontal tube and another is situation of a vertical tube. So if we talk about a horizontal tube, typically at the entry point my fluid will be in the single phase. So it means it is in liquid state. And if it is close to the saturated condition and this surface of the tube is subjected to some heating. So from here we are actually heating this surface. So typically the temperature of the surface has to be greater than the saturation temperature, then only boiling will be taking place. So we have to heat in such a way so that the surface temperature of the tube is greater than the saturation temperature. Now whenever this fluid is flowing, of course at the entry point it will be having some pressure, and at exit point also it will be having some PO. So typically whenever we study the internal boiling, we will be having some delta P. Now it may become say difficult to understand that how to define saturation temperature. Of course for exactly locating the value of the thermodynamic state, we can refer to the local pressure and local temperature conditions, but globally if we have to define the saturation condition for the entire tube, we can simply take the average of this pressure to define our operating pressure, and corresponding to that we can obtain the value of saturated temperature. Now whenever we will be having the refrigerant which is flowing inside this, or any working fluid which is flowing inside this tube, because of the external heating we will be finding that there will be nucleation at the wall of the surface. So all these small bubbles will disengage because of the flow, and because of the flow of the liquid these will be moving in forward direction with the liquid. As we will be moving away from the tube, we will be finding that large number of bubbles are coming from different portions. So all these bubbles will be having chances to join each other and form the bigger vapor volumes. And because the tube is located in horizontal direction, so here gravity is acting like this. So because of this we will be finding that vapor volume being lighter in density, it will be staying mostly in the top portion of the tube. And if you see the cross section, here also you can see in this cross section the bubbles having larger volume, these are staying close to the top, and bubbles which are just nucleating from the tube, these are available in most portion of the tube with smaller sizes. Similarly, in this plug or slug flow type of situation, we will be finding that large chunk of the vapor is staying at the top, but small vapor volumes are actually nucleating from different portions of the tube wall. And as long as this vapor chunk, multiple vapor chunks will be joining together, these will be forming a vapor core at the center, and there will be liquid which is adhered to the outer periphery of the tube. And in the outer periphery of the tube, we can see that the liquid volume at the bottom side, or liquid thickness at the bottom side, will be more in comparison to the liquid thickness at the top side, again because of the gravitational field. And this structure is, these interfaces are actually quite random. So because of these random interfaces, what we will be finding, some instabilities can grow on these interfaces, and because of these instabilities, some liquid can get detached from the film. So, now the liquid will be diminishing in two ways. One is by evaporation from the interface. So, there can be evaporation from the liquid vapor interface, and other can be because of disintegration of liquid volume due to instabilities. Whatever the liquid volumes will be disintegrating, ultimately these will be entering into the core and will be moving with the vapor. So, while these are moving with the vapor, so all these portions are nothing but my disintegrated liquid volumes. So, these are the liquid droplets which are then finally moving with the flow. So, here you can see that the flow has shifted to annular regime, and along with that annular flow we do have the formation of some liquid droplets which are now further travelling with the vapor as the continuous medium. So, this type of flow is typically referred to as mist flow. After the mist flow, once all the liquid has actually vaporized, then we will be finding that we will be having actually single phase flow, pure vapor. One important point we have to understand that whenever we are moving from this portion to this portion, at the entry point we were having purely liquid, and at the exit point we are having purely vapor. So, it means at entry point quality is 0 and at exit point quality is 1. Now, if you look into the density value of water, so density of water is 1000 and density at say atmospheric pressure condition, and the density of the vapor is close to say 2 or 3 kg per meter cube. So, you will be finding that almost there is a density jump of close to 400 or 500. So, in order to operate this under the steady state conditions where the amount of mass moving at each cross section is same, we will be finding here velocities will be at the inlet portion, velocities will be extremely low, and near the exit portion velocities will be extremely high. And as we are moving from inlet towards the outlet, along with increase in the quality, the value of velocity is actually continuously increasing, and in the annular flow regime we will be finding when large amount of vapor has generated, this vapor velocity will be excessively large in comparison to the velocity of the liquid. So, typically we will be finding that this liquid vapor interface will be subjected to a large velocity difference, which will be leading to Kelvin-Helmholtz instability and formation of the droplets. Along with that, the heat transfer from the film will be more in comparison to the heat transfer from the wall. So, we can say that the inlet portion of the tube is majorly dominated by nucleate boiling. So, up to even somewhere up to this, we can say, here you can see this majority portion is actually dominated by nucleate boiling, where wall nucleation is actually participating in the boiling process. But after this point, we will be finding that velocities are excessively large. Because of these excessively large velocities, the wall nucleation will not come into play. Majority of the evaporation will be from the interface. So, film evaporation will be actually taking place. So, here we can see the annular film flow evaporation will be dominant. And after from this point to this point, we may have combination of the nucleation as well as the evaporation. Now, it is also interesting to note that whatever the liquid droplets are left with the vapor, how these are actually getting evaporated. So, ultimately what happens, because this vapor in the single phase regime, after getting converted into pure vapor, it starts superheating. So, because of its superheating, the temperature of surrounding vapor will be more in comparison to the liquid portion. So, there will be again the evaporation from the interface. Other than that, if temperatures are excessively high, then along with conduction and convection effects, these liquid droplets can also face some radiation effects. So this is the reason you will be finding that in nucleate boiling regime, our heat transfer coefficient was increasing, but whenever we entered into the film boiling regime, then it has excessively increased significantly, and it reached to the highest value. After this point, it again started decreasing. So the reason for decrease is, whenever we are operating in a horizontal flow configuration, the significant portion of the tube is actually covered with vapor. So that's why, because of the low conductivity of the vapor, there will be decrease in the heat transfer rates, and majorly the heat will be transferring from the liquid portion. So this is typically the flow boiling regimes with quality inside a internal tube. Now if we talk about flow boiling regimes for vertical tube, where mixture of liquid and vapor is flowing in the vertical direction. So in this direction, initially if I say the pure liquid is in the subcooled state, then first temperature of the liquid will be rising and it will be going to the saturated condition, but locally the temperature near the wall will be larger in comparison to the temperature in the core. So what I can see, even in the subcool regime, there can be nucleation of bubbles in the form of small bubbles, and when multiple bubbles will be rising, these will be forming big bubbles, and these big bubbles will be containing some liquid chunks in between the two bubbles. And in this process, one important point is that situation is almost symmetric. So in case of a horizontal pipe, the wetting of the periphery of the tube was actually not complete, but in this case the wetting will be almost full. And again we will be getting some churn flow and then annular flow and the similar regimes. The only difference is, here everywhere almost wall is symmetrically containing the thickness of the liquid film. And when we operate this, so typically for a upward flow of liquid and vapor, so over here one refrigerant is considered, which is R134A, and it is operated at 338 kilopascals, having saturation temperature of 277 Kelvin. For this, these flow regime maps are presented, and in these flow regime maps we have two important parameters. One is rho L into JL square and another one is rho V into JV square. So basically, if you see the units, it is representing the mass flux of liquid and the vapor. So what is JL and JV? Let me explain to you these two terms. So these are nothing but the superficial velocities. So if you know about superficial velocities, then probably I will not discuss. If, say, for some of you this term is new, then let me explain it little bit. Maybe I will give a brief idea about superficial velocity as well. So whenever we deal with the multiple fluids in combination, we may find that at a particular cross section, the portion of the tube is filled with the liquid and a portion of tube is filled with the vapor. But whenever I will be referring to some another location, I may have a situation where the portion covered by vapor is different now and the portion covered by liquid is different. So typically in a multi-phase flow situation, we will be finding that at each and every cross section, you have seen in the previous photographs also, at each and every cross section the amount or area occupied by vapor and area occupied by liquid is actually different. So in these scenarios, it is extremely challenging to determine the actual velocity of the fluid. If you have to find actual velocity of the fluid, you must have flow rate divided by area occupied by liquid for, say, liquid velocity VL, and if you have to define vapor velocity, you must know VV is equal to QV, flow rate of the vapor divided by area occupied by the vapor. Now if you have some copper tube where at different locations you cannot tell that how much area is occupied by liquid and how much area is occupied by the vapor. Then it is actually difficult to characterize this type of flows. So what can be done? Instead of using the individual areas covered by the phases, we can define this velocity, we can define some velocity parameter based on the total area of the tube. So I can consider what is the flow rate of the liquid divided by total area of the pipe, and I can define flow rate of the vapor divided by total area of the pipe. So this particular term is something which is called as actually superficial velocity. So if you refer to the literature of multi-phase flow, you will be finding this term is actually being used widely. So depending upon the velocities square and then multiplication with the density, so this is becoming nothing but, sorry, this is not mass flux, but it is momentum flux, because superficial velocity multiplied by density will be becoming mass flux, and whenever we are further multiplying with the velocity, it will be becoming momentum flux. So in terms of superficial parameters, whenever we are defining the momentum flux, then for different fluxes, if we maintain, we can obtain this different types of flows. And typically for this particular case, you can see the starting is taking place somewhere in the bubbly slug regime, where quality is 0.01, and then it is moving through churn and annular flow. So this is the route for boiling of refrigerant, and these are the regimes which are actually participating in the transition process. Now whenever we do operate in the internal flow conditions, then we can have again different type of heat flux conditions. Either we can have extremely low heat flux condition, we can have moderate heat flux conditions, or we can have excessively high heat flux conditions. So typically the two regimes which I presented over here, these are valid for low to moderate heat flux conditions. Whenever I will be shifting to the extremely high heat flux conditions, for example, even we talk about in case of this leaden frost effect, if temperature is excessively high and we spray some water, that will be actually floating over the heating surface instead of actually wetting the surface and evaporating. So likewise, whenever internally we will be subjecting our system to extremely high heat flux conditions, what we may experience that some of the regimes which we studied, these can even vanish. So this is one regime which is plotted in terms of bulk fluid enthalpy, and on the abscissa and along ordinate there is heat flux, and it is having certain phase boundaries. So here you can see this boundary is representing the transition from single phase liquid convection to subcooled nucleate boiling. So it means that if you are slowly heating the surface, the required degree of superheating may not occur for a nucleation site, and the liquid will just keep on heating in the forced convection single phase regime, and once it is saturated, after that bubble will be forming. But if you go to slightly high heat flux condition, because of the high heat flux condition, what will be happening? The liquid which is there in the immediate vicinity of the wall, its temperature will be becoming so high that the nucleation sites at the wall will be actually activating, where bulk of the fluid is actually in the subcooled state, because temperature profile inside the tube will be something like this. This will be for, say, extremely high heat flux condition. But if your heat flux condition is not extremely high, profile can be like this. So the temperature near the wall is not much. So gradually liquid is actually heating. Once liquid is gradually heating, then the transition from single phase to nucleate boiling will be taking place later. But if I go to high heat flux condition, then nucleate boiling can come even in the subcooled conditions. And how I am saying that this is in subcooled condition? Because this is my enthalpy value corresponding to x equal to 0. So, this point is actually saturated liquid, and this point is marking our saturated vapor condition. Okay. So, here you can see that when I will be operating at the low heat flux conditions, single phase, because of this single phase liquid convection, will be then transferring to the nucleate boiling regime, and then it will be transferring to the two phase forced convection boiling, and finally it will be entering into mist evaporation regime, and after mist evaporation regime it will be going to single phase vapor. One interesting point you can again observe that my bulk enthalpy is becoming, so quality is becoming 1 at this point, where if bulk enthalpy is 1 at this point, what it means? I should be having saturated vapor at this point, and after this point there will be only vapor. But if you see the transition boundary which demarcates that single phase regime, that is having bulk enthalpy value slightly higher than the enthalpy corresponding to the saturated vapor. The reason is, along with the liquid, along with the vapor, in the core there can be small droplet mist which is present. So, even though, because if you will be putting a thermocouple over here, say close to the wall, that thermocouple will be giving you the temperature of the vapor medium. It will not give you the temperature of the liquid droplet. So, ultimately you will be getting an idea that bulk of the enthalpy has value equal to saturated vapor, but actually there can be presence of small fine droplets of liquid present in the vapor core. So, because of which this complete single phase vapor transition regime will be slightly higher than the actual value of bulk enthalpy. And if you go to moderate heat flux conditions, then as I already told you, we will be getting faster nucleation, which will be leading to the subcooled nucleate boiling. Then we will be having saturated nucleate boiling dominant regime, and finally we will be entering into mist and the single phase vapor regime. If you go to even excessively high heat flux conditions, so when we go for excessively high heat flux conditions, then we will be from the inlet itself, we will be finding that large amount of vapor will be generating, and before the vapor can actually further transfer with the liquid, the vapor bubbles will be merging with each other and forming a continuous vapor film around the periphery, and we will be immediately entering into the subcooled film boiling regime. After with the progression, because temperature will be then radially traveling, and we can get saturated film boiling, and then after mist evaporation we will be entering into the single phase regime. So, this particular curve was applicable when the wall heat flux conditions are controlled. If instead of wall heat flux conditions, I go to the isothermal tube wall conditions, that I maintain the tube temperature at certain conditions. So, here we will be finding that, because one major change is, because nucleation of the bubble always occur at surface temperature with finite amount greater than the saturation temperature. So, this is the limit for onset of nucleate boiling. Up to the temperature value, this limit is not crossed, we will not be able to see any boiling, and once this limit is overcome, after that only we will be able to achieve the boiling. So, most of the things are same, almost same kind of regimes we are obtaining, but the major difference is near the extremely low surface temperature conditions, where we will not be able to achieve this. Okay, so maybe I will stop now. So, though I had included some point related to natural circulation flow loops, if time is available, I will discuss this in the next lecture. Otherwise, I will be providing it as a reading material for you. Okay, so maybe we'll stop now. Yeah. So, I can take the questions if you have. Slowly, and recently I have started working on boiling heat transfer. Yeah, not much. But okay. Yes, yes. All these people are from actually bark. So this natural circulation flow loops, mostly bark people have done this. Yes. You will be finding all these sources we have listed actually. There it is given in even more detail.
So this instabilities that you talk about, people have looked into it extensively, is it? Like from the Kelvin Helmholtz point of view?
Yes, Kelvin Helmholtz, because whenever actually the value of critical heat flux is predicted, that is based on the Kelvin Helmholtz instability model.
Like, so the ideal condition would be in that heat exchanger, everything gets converted, right? That
Yes,
would be there.
yes,
And so you say sometimes the mist will be there.
yes,
That
yes,
is not the ideal condition.
yes,
So
yes. So it means that if we have to fully convert, that where our bulk enthalpy is becoming equal to that of saturated vapor enthalpy, after that point also we should keep on heating to some extent in order to get the completely pure vapor.
yeah, as you said, it was a very nice summary. I really enjoyed it.
Thank you.
So even the subcooling, I didn't know that subcooling. So that book is very good.
Yes, yes. This yes, yes. Van P. Carey is very good, and even for undergraduate, probably this John Leonard is good. So they have also summarized well. Even this both instabilities John Leonard has discussed. Yeah. Yes. Sorry. After, okay. After transition, nothing you have done. You have actually controlled the heat flux, and after that you found that the temperature of the heating surface has suddenly jumped from this point to this point. And after it has reached to this point, then again you keep on heating. The only thing is that you have to take the heater surface temperature in such a way so that its melting point is not actually in this range. Its melting point should be significantly higher than this range. And mostly if you have to do this, then what you can do, instead of operating with water, you can operate with organic liquids, because organic liquids typically have low boiling point in comparison to water. Okay, maybe so if there is no point then.